morning section. So the first talk will be given by Fabio. It's on the full evolution of immediate splitting beyond the soft approximation. So yeah, please go ahead.
Okay, thank you. Thank you for allowing me to talk about this. This is some ongoing work. It's very recent, we haven't really finished all the calculations. So I'm not going to be showing the pretty plots like Carlota was doing in the previous talk. What I'm going to show is what are the steps that we're taking to make a more general calculations. What are the problems that you encounter on the way, and how you can formulate this evaluation of splittings beyond the soft limit. So we're almost there. We hope to have better results very soon, but bear with me. The talk is going to be a little bit technical, but I'll try to make it as understandable as possible. So as Carlota was discussing before, we want to go beyond this limit. Okay, I should have put in this slide when I put this. Z is the energy fraction that is taken by a radiated gluon. So we have done this sort of calculations where you imagine a hard particle that is emitting soft gluons for a very long time, where we look at how these interactions with the medium induce this radiation, and the soft limit is convenient for the energy loss calculations, because if the splitting is soft, you know which is the hard particle that you follow, and you know which one is the radiated particle. If you have a Z that is closer to 1/2, then you end up with the struggle of having to choose one particular path on your Parton shower, and it's not as straightforward. So energy calculations fit into this limit of soft radiation, and we always say that soft radiation has some soft enhancement, and so this is the sort of calculation that we have been doing. It's also much easier, so it's convenient. But now, when you switch to looking at jets, well, you look at different kinds of problems. You still assume that you have some sort of soft radiation that comes from the full jet. If the jet is narrow enough, you imagine that it can still lose to some first approximation. It might lose energy as a single object, but of course you should look into more detail and do calculations about that. But what we also need to look at these harder vertices or these harder splittings, and try to see what happens when we zoom in and look at that. And like Marta was telling us, we want to look at this structure. What is the distribution of this Z variable of the fraction of energy that is taken by one of the particles? And we want to be able to do this kind of computations where we look at what is the medium modification of a vertex with any fraction of energy. So before I continue, just let me clarify what is the formalism that I'm using here. So we are in this multiple scattering formalism, in which we assume that all the partons have a large longitudinal component for the momentum, and all transverse momenta are much smaller. This is this sort of collinear approximation, in which you can sort of decouple longitudinal and transverse dynamics. And therefore, when you look at what happens with the medium, you can do, as Carlota was showing, what is the evolution in the longitudinal direction. But we always do like something kind of trivial in the transverse component, and that's justified by the fact that the terms that come from the transverse dynamics are usually suppressed by the energy of the partons. And going beyond this limit is what will be talked about in Andre and Joao's talk, and I think it's Wednesday. So because of this decoupling, we can work in this mixed representation where we always have the longitudinal coordinate. We call it time. It's actually a plus coordinate in the longitudinal direction, but in transverse space, we switch back from coordinate to momentum space. In this talk, I will talk, everything will be done in momentum space. There might be some a quick reference to coordinate space, but most of the calculation is done in momentum space. So we resum multiple interactions by using these propagators in a background field, where we resum field. We have a background field A minus that I put there, and it's a resummation of insertions of this field of how a parton can interact with this. And then we have also vertices for the splittings that are like vacuum splittings. And so depending on what is the identity of the particles, I'm doing this in general for the moment. It can be a quark going to a quark gluon, a gluon going to a quark anti-quark, or whatever. What is important is that there's some vertex factor that has a very particular dependence on the transverse momenta in this collinear limit. It depends on some particular combination of how the moment here. There's conservation of transverse momenta in this vertex, but the dependence on the vertex is on this particular variable. And I wrote the color factor explicitly. And then what we do is that we calculate this for a background field, and we take averages over the background fields. And the simplest model that we can imagine, and is what everyone uses, is this Gaussian correlations, in which you only the only non-trivial correlator is the correlator of two insertions of the field. But this induces correlations between different in-medium propagators in general. And that is what complicates the calculations. And what is important here is that there will be always, when you have a particle that is scattering with the medium, there's a color flow into the system, but it always gets compensated when you look at everything that happens in the amplitude has to happen in the conjugate amplitude. So when you look at cross sections, there's some sort of color triviality that is always there. The same with the conservation of momentum, and we'll get into that later. So just very quickly, what we do with these in-medium propagators, well, there's a formal expression for it in transfer space. I won't get into that, but people are familiar with this, so I put it there. What I would really use is this sort of equations, either this like Schwinger-Dyson type equation, which graphically looks like this. Like if you have a propagator, it's like the vacuum piece plus a little bit in the vacuum and then an insertion convoluted with the rest of the propagator. You can also write this in differential form. And we have some convolution relations for this propagator, which more or less what it tells you is that you can, if you have propagator, you can slice it in two whenever you want. And also if you have a propagator and a conjugate propagator, if you integrate over the final momenta, then they sort of cancel out. I will show this graphically later, how we use this sort of properties. So we look at this sort of splitting process where we have some vertex. Now I'm going to stop drawing everywhere the interactions with the medium. So now there are always interactions with the medium. I just don't put them explicitly. And so just to set the kinematics, here you have three in-medium propagators in between the different times that we set, and vacuum vertex. And but we always do square this, so I will always use this sort of diagrams in which I put my conjugate amplitude right next to the amplitude, because we want to keep track of the longitudinal coordinate and what happens when. And so we always have this sort of diagrams where now I have 6 propagators, and it looks a little bit complicated. You have to take averages. These averages, what they do is that they contract these field insertions into different propagators and induce some correlations between the different particles. And so the usual approach, what we always do with these things, is to think about the different regions in terms of the variables, what happens before T1, what happens between T1 and T2, what happens after T2. I can do that because the averages that I'm taking are local in time. So we do things like this. We look, for example, at this line here. There's going to be a propagator here. There is this one that is written here, and I slice it in 2. So I can use these convolution properties to look at only in the region that I care. And the same can be done with, for example, with this red one here, or this green one here, which is this one here, this one here. So at the end, you end up having lots of propagators that you want to take the averages. But the nice thing is that you can factor out those averages. So as I said, so I only care of, I can look at the regions separated between this T2 and T1. I can look at those regions separately. And as I said before, these averages also, the flow of color always goes from like the amplitude to the conjugate amplitude. So if you look at this overall picture where you have all the particles in the amplitude and the conjugate, there's a color conservation. There's the full state has to be in a singlet state. And also there's a momentum conservation in the sense that like the sum of the momenta in the amplitude always have to be equal to the sum of the momenta in the conjugate amplitude at any given time. And that's very nice for calculations. Okay, I forgot to say, but a lot of what I'm saying right now is actually work that was started like 10 years ago. I have the references down there. This is not entirely new. I want to show it in a slightly different way, which is more amenable to what I want to do later. So anyway, so if we go looking for region by region, like this is initially this is the simpler region. So the emphasis that I want to put on right now is what are all these momentum variables that I have, because like everything that it's all the momentum variables in between, everything except the k and the q at the very end is going to be integrated over, are just dummy variables for what is going in between. So because I have this conservation of momentum between the amplitude and the conjugate amplitude here, I have no choice. I only have one momentum on the left side and one momentum in the right side. And actually, because the interaction with the medium, the exchange momentum doesn't really depend on what is the transfer momentum of the the particle. Then this when I calculate these averages, it depends only on the difference between P1 and P0. So in principle, when we have these two particles with the initial state, final state, it looks like you could have up to 4 different transfer momenta, but actually you only care about one momentum variable for this particular average. Then if you move to the next region, it looks like you have 6 different transverse momenta, but of course there are some constraints that the sum on the particles in the amplitude has to be equal to the sum of the momenta in the conjugate amplitude. That reduces into the number of independent variables. And also, if I'm looking at the sum of the momenta, then I should complement that with the relative momenta, which I write it like this, which is the same as that momentum variable that appeared in the vertex factors. So instead of using K1 and Q1, I will use P1 and L1. But also among those 4 momentum variables, I only care about 3 of them because I only care about the total momentum. The only thing that is important is the total transfer of momentum in that region. So I define some new K function, which I'm not saying explicitly. It's calculated from those 3 propagators, but I will get into later how to calculate that, but the important thing is that it depends only on these 3 variables. And then in the last region, I also have the same, some constraints in the momenta, and I also switch to relative momenta. So in principle, it looks like you have 6 different variables. You have 1 constraint, which reduces it to 5. But actually it depends only on 4 of those variables because it's the same thing. It depends only on the total transfer. So when you put all this together, you get some big expression that have all these correlators, which you still have to calculate. But then you have here, this is like a D-Glab splitting function, depending on the identity of the particles. These factors here comes from the vertex factors. I already sum over all the polarizations and everything. And then you get like a convolution between these things. Some version of this was already in these papers. And then, okay, you arrive at this complicated expression and you don't want to get into this calculation of these complicated averages of propagators. So you have to figure something out. So back then in 2012 and 2014, there are those 2 papers there. The approach was like, okay, let's look at some approximations. Everything was done in the harmonic approximation. And then in some version of a largency limit. And either we said something like, okay, If we consider short formation times, maybe like this, you look at these particles, like this particle is flying away from these other particles, so the correlation between them are not that important. And we decided to like try to look at particular limits in which you can simplify the structure of all these correlations. And this other paper by Liliana and collaborators, they went a little bit further. They wrote some like more complicated and complete expressions in the largest limit. Well, with the hope that somebody will solve it numerically at some point and do something with this. And nobody has done it so far because it's way too many variables. We don't really know what to do with something like this. It's a double differential cross section. I don't even know what to plot if I were able to calculate this, how to put it in a how to show me my results. So okay, so what we do is like maybe double differential in my two final particles is too much. So maybe we can look at some limits. So first, okay, we know the soft limit, how the soft limit emerges from here. If we say that we take this very particular limit in which like C goes to 0, but the energy of the emitted particle is finite, doesn't go to 0. It's a very particular limit, but this is what we do in practice. It's like, okay, it's like the hard particle is like a straight, the angle of the emission depends only on the transverse momentum of the soft particle, and everything starts to look a little bit easier. If I put the amplitude and the conjugate amplitude together, when I take this limit, like actually the hard part on the two lines lie on top of each other, and there are cancellations because of the color trivial. Those red propagators at the end or these green propagators at the beginning cancel out, and the one in the middle actually becomes purple. This is I don't want to get into details, but this is the calculation that Carlota had a very similar diagram of what was going on there. You split it into different regions of some emission kernel and some momentum broadening, and we know how this works out. Okay, so our calculation is consistent with that. That's fine. You can also just say, okay, this is too differential. Maybe I can integrate over some of the final particles. So if I say, okay, I integrate one of them, I integrate over this transfer momentum Q, and I remember that I had like some convolution properties for these propagators. So actually that last part of the red particle doesn't contribute. I get this simpler diagram where it only depends on K. But the problem is that here K doesn't give you all the information about the splitting. You lost information about what is the splitting angle, and is really not that useful to have explicitly that variable K once you have integrated the other particle. So, okay, so let's integrate it too, because it doesn't give you much. So it simplifies it even more because you lose like those purple propagators at the end. And actually you do lose also the broadening at the beginning. I will explain that a little bit further, how that happens. And when you calculate those diagrams, that gives you just the energy spectrum. And this is something that we know how to do. We actually, calculating this is not much harder than the calculations that Carlota showed in the soft limit. And so we can easily generalize that for a finite Z, only this one, that you already lost all the information about the transverse dynamics. So none of these simplifications will tell you anything about the angle of the splitting, for example, which is something that we would like to do, which is something that we would like to emphasize it. So how do we isolate that angular dependence? So if you look at the kinematics of all this here, the angle depends on that particular combination of the variables. It depends on the magnitude of that relative transverse momenta. So again, so we do this change of variables that I already wrote before. We'll look, instead of looking at K and Q separately, we'll look at the relative momentum and the total transfer momentum. And then, so I had written this complicated expression before. So instead of writing here explicitly this K and Q in this here, let me just put it in terms of L and P. And then if I say that what I want to keep is the angle, then I don't care about this capital P. So I integrate over this capital P, and in the right-hand side of the equation, it only enters on this particular function S4. So I can just shift my variables and just integrate that part. and I replace that by an integrated S4. I just put a tilde on top of it to just say that I integrated over that. And then you realize that, for example, when you look at now at this P2 bar variable that I had before, it only enters on the K3. So I can do the same, and I can replace that K3 by an integrated version of that K3. And then the same thing happens now with the P1, that the P1 enters only now on this initial broadening of the initial particle, and the integration over these broadening distributions is 1, so it goes away. And then it's my expression is a little better. It looks a little more compact. Now also, sorry, I should have said here that after integrating over P1, then I can integrate over P0, which will only affect that hard cross section. So I also integrate that, and then I find this expression, which is a little bit more compact, has a lot less variables, but still it's. Yeah, I still have to deal with this S4 and this K3, which still I have to go and look at averages of 4 propagators, average of 3 propagators. I can even go a little bit further, because I only if I'm looking at if I care about the angle between the 2 particles. So this sounds a little counterintuitive, but that means that you care only about the magnitude of L, so you can integrate the angle of L. And I didn't write it explicitly because it looks prettier when you have 2-dimensional vectors, but you can get rid of an additional angle variable here and reduce the number of variables that you have everywhere there. Oops, sorry, I touched something here. How do I stop this? I don't know. What did you press? I touched something in the tablet.
Well, I'll go ask for it. Maybe you can try it out. Okay.
The rest of the seminar is Blackboard.
Okay.
I don't know what I
help
did.
is coming, so okay. Probably not a good idea to touch even further.
Okay, so I can continue talking a little bit. So anyway, so now you have to do something. I touched the tablet. I don't know what I did. So we need to find ways of either find suitable approximations to those expressions, or just try to calculate them. Right? So there was an approach that we tried a few years back, which is just doing an approximation for these in-medium propagators and saying, okay, this in these medium propagators, you let the particle move in transfer space. There's if you look at it in coordinate space, there's like a path integral there that you have to do something about it. So you can just say, okay, I'm going to assume that I have high energy particles and do like some sort of saddle point approximation to my path integrals, and then which is more or less saying that your particles in coordinate space will go in like a straight path. So we tried that some years back, and we did it for one simple case. It's coming. Which was just because it's the simplest thing that we could do at the time was taking this gamma to QQ bar, and which is not really what you want to do, but it tells you something about the sort of the results that you can get. And in that case, you can do like a long plane for the emissions and see if it corresponds. Those lines that we had in that plot was like estimates that we had from just qualitative arguments of where we thought that the encasement will be. And so we did that, but then Conrad and Johannes took this one step further. They did without the largency approximation for all sorts of different splittings, and you get some results for that. But okay, so that's some progress. But now we don't want to take this what we call this tilted Wilson line approach. We want to do some way of calculating these averages of this. An idea was in this paper was of like calculating this by like writing these differential equations for the correlators. By doing a little step in the longitudinal direction, we can do the same thing. So when we calculate these medium averages, as I said, we use this equation for this form of the propagator, but and we just contract these emissions of the field. And what you see is like if you take two propagators, we already know this is the usual momentum broadening calculation. It looks like an expansion like this. You only care about this particular term where you have one interaction, and you can write that in this type of integral equation, or you can take the derivative, write it as a derivative on T1, and you can solve this. You can do numerics for this. So, I mean or you can just go to, in this case, it's easier to go to transverse coordinate space, but anyway, you can also solve it numerically in momentum space. If you go to three propagators, then you have to take all the possibilities in which one interaction can reshuffle everything, but colors is still trivial because you have only one overall singlet state when you have three particles. So each of these possible interactions does not change the singlet state that you have for the overall combination of the three particles. You have to be a little bit careful with the phases because remember that the propagator had these phases, and you see that it depends only on that relative momentum, as we had said before. Now, if you look at the interaction, it has like some form that I put the deltas here to put them how the momentum flows, and so. But in terms of the relative momenta, it looks something like this, and you can write some similar expressions to what we had before. This is the integral form or the differential form, and this is something that you can solve numerically. And then when you go to four propagators, what happens is that you get more terms. Now, color is not trivial because now you have several singlets depending on which state you have. So what you have to do is that you have to define a basis of that singlet space and project into that singlet space. So just very quickly, and I'm about to finish right now, again, instead of putting all these variables, you do a convenient change of variables to put in terms of this, in terms of the relative momenta. The difference of the momenta between the amplitude and conjugate amplitude is always 0, and we integrate over the total momenta all the time. So we reduce this thing to some object that depends only on this relative momenta. This with like open color indices that I'm not writing. And then when you project into some basis for the singlet states, you can write some evolution equation in the longitudinal coordinate where this factor T that I am writing here is it just comes from the sum of all these interaction diagrams. I mean, you can work it out. That's it's long, but it's not that hard. And so you can solve for this S function, and then the one that we actually had was like a particular color combination of this. So if you know all the S's, actually you only need to know one color state in one of the ends, and then on the other one, and that's it. So what we end up doing is reducing the number of variables to the bare minimum that we can have, and write some equations that you can implement numerically and that you can feasibly put it in some code that is going to solve it. We're in the process of doing that because when you increase the number of variables, all these convolutions means that you need lots of memory and you need to get more sophisticated methods of doing that, and that's why I don't have results yet. But but that's the recipe. If anyone wants to go and do it faster than what I can because I'm a beginner on this, please go ahead. I will put this public soon. Thank you.